Welcome class to our section 2.5 video notes, where we have now done 2 in-class discovery days using GeoGebra, 2 in-class discussion days as a class discussing the patterns we observe with GeoGebra. So now that we're actually officially doing these notes, this is really just kind of making it official. We've already discussed all the stuff we're about to do for 4 days already. So with example 1, we're just doing simple shifts, starting with this parent graph. So I think what I'll do is I'll sketch the parent graph. It's always really good to get the parent graph sketched first and then start doing the transformations. So I'm just going to pick a couple points off the parent graph of x squared. Maybe I'll do a couple more. So at 2 it's 4. And at -2, it's also 4. So we get this parabola shape. It's very important that you understand it's not a V. The x squared parent graph is a parabola. And it's very important to be as precise and detailed as you possibly can. So there's the parent graph, and now what we're going to do is sketch the graph of x squared plus 2. Which is the same shape as the parent graph, but it's shifted up 2, which literally means you add 2 to each of the y values. So instead of being at -1, 1, you'll be at -1, 2. Instead of being at 0, 0, you'll be at 0, 2. I'm sorry, you'll be at -1, 3. My bad. Instead of 0, 0, you'll be at 0, 2. Instead of 1, 1, you'll be at 1, 3. And at plus and minus 2, both of these points will be up at 6. And so it's the same shape, shifted up 2. And then it's the same thing in part B. It's still a vertical shift, but it's shifted down 2. So you subtract 2 from each of the y values. So here's the parent graph. And you would subtract 2 from each of the values. So it's like you take these points and just literally move them down 2 units. Now I just want to point out something here because this makes graphing so much easier for me, and so I just thought I'd point it out to you, and maybe it'll make it easier for you too. Basically, when I'm sketching graphs like these that only have shifts, instead of like moving each and every point, what I do is I just look at the parent graph, which is x squared, and then I just look at the shift to see where it's starting. I just go over to where it's starting, and then from there I just graph an x squared graph. Like for example, what I was doing here is if you look at the graph of x squared, to get to the next 2 points, you go over 1 and up 1 on both the left and the right. And then to get to the second point, you go over 2 and up 4 because 2 squared is 4. So I literally just did that here. I went over 1, up 1, and then over 2, up 4 to get like the next 2 points, and then I did that on both the left and the right. And it only works, of course, with this particular parent graph because it's a squaring parent graph. So like if I wanted another point, I could go over 3 from the starting point and then up 9. And that would give me another point that's still along this graph because 3 squared is 9. So if I go over 3, I'd go up 9. It's just kind of like a feature of x squared. So actually that's how I graph these. I just drop down 2 and then graph an x squared graph as if I were at the origin. So I go over 1, up 1, over 2, up 4, over 3, up 9, and so on and so forth. Okay, so in example 2, what we'll do is go in stages. So the final answer will be this graph right here. And we'll start with the parent graph. And this is how I'd like you guys to sketch your graphs, is in stages, starting with the parent graph, ending with the final equation graph. So the parent graph, of course, you look for what the equation is saying. The equation is saying you take your input and you square it. Okay, so that's how I know the parent graph is x squared, because that's what's happening to the input of this function. So I'll graph the x squared parent graph. And that's the one that's 0, 0. You go over 1, up 1, over 2, up 4, over 3, up 9, so on and so forth. And then I'll go ahead and do my horizontal shift. So you just have to remember when it's a horizontal shift, you always do the opposite. So we're going to sketch the graph of x minus 2 squared. So just be really careful with horizontal shifts. We're actually going to shift to the right 2 units. And the reason for that is because I want to keep the y values the same. Like I'm changing x, but I'm keeping the y values the same. So the y value should start at 0. So in order for y to equal 0, then x has to actually be positive 2. Because positive 2 minus 2 will give you a 0. And so that's why you always move in the opposite direction, because you're trying to cancel out that minus 2 to make a 0. So you have to move to the right 2 to cancel out minus 2. So you start there, and then from there it goes over 1, up 1, left 1, up 1, over 2, up 4. Or you can literally think of it as taking this graph and just sliding each x value over to the right 2 spots. But then we still have this minus 3. So this will be the final graph. So we take the points here and we shift them down 3 units. So I have a point here at 2, 0. So then I'll shift that one down 3. I have a point here at 3, 1. I'll shift it down 3. And then I'll go over 2, up 4. And here is my final graph. Now notice, I never changed the shape of this graph. I never stretched it or shrunk it, so it never changed shape. It's the same looking parabola the entire time. I just shifted it to the right 2 and then down 3, and so this graph is my final answer. Shifted right 2 and then down 3. And from there it has the same shape of a parabola, meaning it goes over 1, up 1, over 2, up 4. Now in example 3, you're given the graph of your function. And let's just go ahead and give it endpoints so that we know where to start and stop our function. So the endpoints are right now at 0, 0 and 3 pi 0. So this is going to be f of x, and then this example wants us to graph 2 times f of x and then f of 3x. So we have to think back to our GeoGebra activity and what does multiplying a number on the outside of a function do to the graph of the function. So hopefully you remember it vertically stretches the graph by a factor of 2. So the way we're going to sketch this graph is we're going to times the y value by 2 of all of these points, and we'll keep the x values the exact same. So this is a multiplication. Maybe I'll just write times y by 2. Okay, x values stay the same. So I have an x value of 0 and a y value of 0 stays the same. Now at the x value of pi over 2, which I guess I'll put that here, the y value on the parent graph is 1, but since we're stretching by a factor of 2, we're going to multiply 1 by 2 and make it go all the way up to 2. And then I have a value of pi 0, which 0 times 0 is still 0. And then at 3 pi over 2, the y value is negative 1, so that's going to get multiplied by 2, and it's going to become 3 pi over 2 negative 2. Then at 2 pi, the y value is 0, so 0 times 0 is still 0. At 5 pi over 2, the value of y is 1, and we're going to multiply that by 2 and make it 2. And then at 3 pi, the value of y is 0, and so 0 times 2 is still 0. So the graph is going to look like this. And this point right here would be pi over 2, comma 2. That point would be 5 pi over 2, comma 2. and that point would be 3 pi over 2 comma negative 2. So the x values did not change. They are still 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. Those are all the same x values. So by the way, our x-axis is going by pi over 2's, since I didn't label it, so we should say that so that it's clear. So this is pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, and so on. Okay, all that happened is basically the y values got multiplied by 2, so it looks like an actual stretch. It's like somebody took the ends of this and stretched them up and down. And so you have this skinnier looking graph. Now, over here in part B, we can see that the number being multiplied is now inside the function. It's inside the argument, or it's being multiplied to the x that's getting input into the function. So because of that, this is actually going to be a horizontal shrink or compression, because whatever you see on the inside, you have to do the opposite. So what's going to happen is we're going to have to multiply all the x values by 1/3, because we're trying to cancel out that 3 so that we can get back the same y values. So let's go ahead and make a table of values. And we want to keep all the y values the same. So if you look, the y values are really just 0, 1, 0, negative 1, 0, 1, 0. Sorry, we're going to have to go down into example 4 down here. But we want to plug in the x that once I multiply it by 3 would give me this x. So the first one's easy. 0 times 3 is still 0. For the second one, pi over 2, what you do is you have to multiply that value by 1/3. So maybe I'll do all that up here. So if I did pi over 2 times 1/3, well, whenever you're multiplying fractions, you just multiply straight across. So really, I need to plug in an x value of pi over 6. So if I took pi over 6 and plugged it in here, I'd have to multiply it by 3, which would make it go back to pi over 2. And then f of pi over 2 is 1. So it's kind of like you're canceling out the 3 by multiplying by 1/3. Then I go to this value of pi. If I did pi times 1/3, think of pi as like pi over 1, I'd get pi over 3. So this x value right here that goes with 0, the second 0, has to be 1/3 of pi over 3. So that if I were to take pi over 3 and plug it in for x, the 3's would cancel, and I'd have f of pi, and f of pi is 0. So I can keep the same y value because I'm canceling out the 3. And so I'll just go through and do the same thing for all the other ones. So I'll take all these x values and multiply them by pi over 3. So let me do that by 1/3, sorry. So let me do that over here. So the next one is 3 pi over 2. So if I multiply that by 1/3, the 3's will cross cancel and I'll get pi over 2. So that goes here, and that was with the value of negative 1. Then here, the value of 0 was when x was 2 pi. Think of 2 pi as being over 1. If I multiply that across, I get 2 pi over 3. So this is the x value that I would need for that 0. Then for this value of 1, I've got 5 pi over 2. So if I go straight across, that's basically 5 pi over 6. And then for the very last 0, that was at 3 pi. So if you multiply 3 pi by 1/3, well, the 3's will cancel out, and you're just left with pi. So what's basically going to happen is this entire graph is going to be all done by the time I get to pi, because all the x's have been shrunk by 1/3. So it's going to be really hard to see this graph. So I'm going to have you be very careful. So what we're going to have, the x-axis is still going to go by pi over 2's, because I want you to see, I want this to have impact on you. So that means this is pi over 2 and this is pi. So the whole graph is going to be done by the time I get here. Okay, so understand that pi over 6 is basically a third of pi over 2. It's what you would get if you took pi over 2 and multiplied by 1/3. So since this little distance here is a pi over 2 distance, if I cut it into thirds, then I could understand this first one would be pi over 6. The second one would be 2 pi over 6, which is the same as pi over 3. So I'll just put in parentheses. It's like the second sixth. And then pi over 2 would be 3 pi over 6. And then I'll do the same here. I'll cut those in thirds, so then I'd have 4 pi over 6, which is the same as 2 pi over 3 if you reduce out of 2, and then 5 pi over 6, and then pi. So I have the points 0, 0, pi over 6, 1, and I'll have the y-axis go by halves again. So every other one is a 1. So that'll be right here. Pi over 3, 0, that's right there. At pi over 2, it's -1, that's right there. At 2 pi over 3, it'd go back to 0. At 5 pi over 6, it would be up at 1, or right here. And then by pi, it would come back to 0 again. So we have this graph here. So I'll go ahead and zoom in on that so you can kind of see a little better what was going on there. So this mark was pi over 6 was at 1. This one was pi over 3. Then when you get to the edge of the square, that's pi over 2. That was down at -1. Then the next little mark was 2 pi over 3 was at 0. And then 5 pi over 6 was at 1. And then by pi, it was back to 0 again. So it's the same shape, or not, sorry, same shape, but it's the same function. It goes up to 1, down to -1, up to 1, back to 0. But it does it 3 times as fast. Or you can say it shrunk. Like it took this graph and pushed it that way, kind of like a spring, and made all the x's shrink back by a third. And so this is the graph of f of x if you multiply the argument by 3. So now here's one for you to try. Here's the graph of a function. And then on the next page, you're asked to graph f of x plus 2 and then half of f of x on these grids here. So I'm going to have you try that. Pause the video right here, try these, and then come back to check your solutions. Okay, so first thing I hope you did was pick out some obvious points from the parent graph, like the x-intercepts are really obvious points. And the y-intercept is an obvious point. Since these are going by 16s, that's probably like 14 right there would be our -14 would be our y-intercept. And then we could kind of guesstimate where that is. It looks like it's at 2, I don't know, 52, -52. And then this one would be at -3, -28. So those are just some standout points that we can use when we're shifting the graph around. So hopefully you guys identified some points and then we're able to shift them. So for the first one, we really only need one grid. We don't need both because we're just doing one change. We're just shifting everything to the left too. So what you might want to do right now is label the y-axis in a similar fashion as the other graphs was labeled. So maybe we'll have this go by 8s so that every other one goes by 16s. And then maybe we'll have this go by half, so like every other one is a whole number. So since the graph is moving everything to the left too, your y-coordinates should stay the exact same, but the x-coordinates would get subtracted by 2. So we'd have a point down at -6, 0, a point at -3, 0, and a point at 1, 0. And then instead of a y-intercept at 0, -14, we would have a point at -2, -14. And then we'd have a point at -5, -28. and then a point at 0, negative 52. And then we could kind of sketch the graph from there. And it's the same graph, just everything was shifted to the left 2. So we subtracted 2 from the x-coordinate. So your graph should look something like this one, depending on how you labeled your axis. For your second try, you should have multiplied the y values by 1/2 or divided the y values by 2. So this one should be look vertically shrunk by a factor of 1/2. So again, it helps if I label the y-axis the same way it was labeled in the other graph, and same with the x-axis. So now in this one, your x values should stay the same, but your y values should shrink by 1/2. So actually all the intercepts would be the exact same. So you'd have an intercept at negative 4, 0, an intercept at negative 1, 0, and an intercept at 3, 0. That all would stay the same. But now the y-intercept, instead of being at 14, would be at negative 7, so it'd be a little bit higher. And then at negative 3, instead of going all the way down to negative 28, it would only go down to negative 14, so kind of where the y-intercept was before. And then the point that was at 2, negative 52, would go to 2, negative 26. So it would kind of look something like that. So similar shape, just shrunk. The y values are only half what they used to be. So it's like someone just took this graph and literally compressed it together. So it is a vertical compression by a factor of 1/2. So your graph should look something like that. So it turns out we didn't really need these because we were only doing one shift per graph.